So if I give you this, it's not very easy to decide whether this is coming from quantum theory or not. And for some applications in quantum key distribution, we need to solve exactly this problem. And so this is what we are going to be talking about today. How to decide whether this is coming from quantum theory or not. And we're going to be looking at this formalism of commuting measurements, which means that there's going to be a quantum state, and then there's going to be a measurement on Alice's side and measurement on Bob's side, and that's it. So no tensor products, but we do this with the assumption, or with the condition, that the measurements of Alice and Bob commute. Or of course, this is the usual commutator. Now, if we had the previous formalism was that this was given by some other sigma AB, and these states, and there was this thing and that thing. But to remind you how to go from this to that, what you do is that you just decompose these into, or you add these identities here. And now we call this the MAX above, and we call this the MBY above. Okay, so we had this kind of tensor product strategies and these commuting strategies last time. If something is a tensor product strategy, this is how you make it into a commuting strategy. But there was this kind of big result that if you have a commuting strategy, it doesn't have to be coming from tensor products of something. And this was a very big result recently, and a few years ago. So now what we are going to do is that we are going to develop some kind of hierarchy that will give us outer approximations of the set of commuting strategies. What this will mean is that we will take this thing, the commuting strategy, we'll assume that the probability that we have is given in this sense. We will derive some kind of necessary conditions, and we'll use these necessary conditions later to check if that actually belongs, if that actually is given by a commuting strategy. So again, it's the same idea as in entanglement detection. You assume this is true, you derive some kind of conditions, and then if you want to check for something else, you just check those conditions. And if those conditions are falsified, then it cannot be true. Okay. Moreover, in this case, we'll get a hierarchy, or there is a hierarchy that's of like ever bigger problems that you can solve, which in the end is proved to converge. And this is the NPA hierarchy that we'll be discussing today. So the NPA, where that stands for Navasquez Neo-Assine hierarchy. And let me just check the spelling of those names. Yes. In order to prove this hierarchy, we will need the lemma that we proved during the last lecture. And this was the following lemma. That we had S1 to Sn to be some operators on a Hilbert space. And U to be a vector in the Hilbert space. And then we defined Rij to be a matrix with elements U, Si, star, Sj, U. And R is the matrix with entries Rij. So this just says that the Rj entry of matrix R is this number Rij. Then R is positive semi-definite. This lemma was the last thing we did before Christmas. And the proof is rather direct, because you just multiply from vector from left and right, simplify, and you get the thing that you need. Okay. So this is all that we need. Okay, we still need to do one more simplification before we actually formulate the NPA hierarchy, because here we assume that we have arbitrary state and that we have arbitrary POVMs. Now this is a little bit too complicated, or this is a too few structure to do something. So first of all, what we want to realize is that instead of rho, we can go to a pure state psi, because we can always purify any state. So we can replace the state that Alice and Bob have by its purification. So without loss of generality up there, we can assume pure states. Similarly, instead of the POVM, we can go to some kind of projective measurement. Now, this does not, strictly speaking, follow from purification, although it's something like purification of a POVM into a projective measurement. And you can find this as Naimark, or also the spelling Neumark dilation. And it's a well-known result that if I have a POVM, I can always find a bigger system on which this POVM can be measured as a PVM, okay? So this just means that you can always have trace sigma MAX can always be made equal to trace of some kind of bigger operator omega on, say, A and some environment, and here you put FA given psi A given X, psi A given X. So based on these two results, we don't have to worry about mixed states, and we don't have to worry about POVMs in this problem. We can just go to pure states, and we can just go to PVMs. So the notation now will be as follows. The pure state that we will have will be psi, and we will have a PVM on Alice's side, so this is PAX, which satisfies the conditions such that PAX is of course positive semi-definite. It's projective operator, so the square of this is equal to itself. And sum over A of PA given X is equal to identity. So this is what Alice has. What Bob has is a PVM QB given Y, which is again positive semi-definite, projector, and sums to identity. So we want to assume we have this conditional probability of this form. By some purification and dilation argument, we go to only pure states and only projective measurements. So this is the state, that's the one measurement, that's the other measurement. What else? Is this everything that we have, or do we have more? Yes?
They commute still?
Yes, exactly. They still must commute. And this is extremely important because, after all, it still has to be a commuting measurement strategy. If they would stop commuting, it wouldn't be that. It would be just some sequential measurement at best. And in this case, we know that PAB given XY is psi PA given X Q given Y psi. Where we all know that if you plug a pure state into the trace here, it simplifies to this matrix element. So, who measures first here, Bob or Alice?
Doesn't matter.
Exactly, they commute. I mean, this is the same. As that, right? Because they commute. Okay. So far this is clear, right? We assumed this thing comes from a commuting measurement strategy. So of this form, some purification dilation argument leads us to pure states, projective measurements, and we get some conditions for that. Okay. Now we can, using this, derive some relations. The first one is that psi identity psi must be equal to 1, which is just a very strange way to write down that psi is a normalized quantum state. The second thing that must always hold is that for any operator m, we must have that sum over a of psi pa given x times m psi is the same as sum over a psi m pa given x psi, and that's psi m psi. Why is this true? If it is true? So why? Yeah?
The last sign comes from that measurements sum of 2, 1.
This one. And this one? If this one comes from measurement equals to 1, then this would be equal to that as well, right? So if I would write here that this is equal to psi m psi, you would believe me by the same argument, right? But then this must be equal to that by transitivity of equality. Because if this is equal to that, that's equal to that, and this thing is equal to itself, then everything is equal to everyone. There's a prime here, so this is a given x, a prime given x. The a and a prime are like two different indices, but the x is the same here. This is the Kronecker delta, 0 if they're different, 1 if they're the same. This is PA given x. Where did I get this one from?
If they project into different subspaces, the result will be 0, right? Because the binding subspaces of the observable will be orthogonal.
Yes, exactly. These are two orthogonal projections, so their product must be 0. That's where this comes from, and this is essentially the same thing. Do you want some kind of explicit proof, or do you just believe me? If I have a projection, then if I do something like p times 1 minus p, then this is p minus p squared, which is p minus p, which is 0. So projection is orthogonal to its complement. Now if I have a PVM with 2 outcomes on a qubit, this already gives me that. Now the question is what happens with 3 outcomes. In this case, you would have projection P1 and P2 such that P2 is less than identity minus P1. What this means is that we have a PVM which is P1, P2, and many other things, which means that we can which means that P1 plus P2 plus something else is equal to identity, but this is just sum of projections, which is positive semi-definite, and so this means that P1 plus P2 are less or equal than identity, where this is just a PSD thing, or this just means that 0 is less than 1 minus P1 minus P2, which is exactly this thing here, which must be positive semi-definite because it's sum of PVM elements. In which case we get that P1 times P2 using the, well, we know that they commute because they live in the same PVM, so we can always write this as P1, P2, P1 or something like that if you wish. And now we can use this inequality here, and we go to P1, and here identity minus P1, and here another P1, but this P1 and this P1, they reduce themselves through this rule, and everything commutes here because they're just orthogonal projections, and we're back there. And this is a positive operator which is less than 0, which is just 0. Now, so you believe me, all of these rules are true, okay, right? So if anybody has any doubts, like speak them now or remain silent forever. But we still cannot use this to check whether PAB given xy has a commuting measurement, can be realized by a commuting measurement strategy, because all of these rules, they explicitly refer to the measurements and the state. Okay? So in principle, I know that if this PAB given xy comes from projective measurements measuring a pure state, that all of this is true, but somehow these conditions explicitly refer to the measurements and the states, so I don't really know how to check that. But they don't refer to them in an arbitrary way. They refer to them in such a way that what we have here are always matrix elements, or always operators sandwiched inside the state psi. And these operators that we have here, they are something like monomials in P's and Q's. Or some people you tend to call these words in P and Q. Okay, because this is one way to talk about this, that you can see this PA given x and QB given y as an alphabet, where alphabet is just some kind of set. So if I have, for example, alphabet ABC, which is just a set, then words in this alphabet would be A or B or C or AB or BA, ABC, ACB, whatever. So it's just something like ordered lists of the elements from that set, words. So what do we have here is that we have all of these rules, but all of these rules reference explicitly to the projectors and pure states, but only in the form that there's always some kind of word or monomial in the projections, and it's sandwiched inside the pure state. This is where this lemma comes in. Because now what we are going to do is that we are going to say, but hey, look, this is also like operators sandwiched inside the pure state. Okay? We can see this as our set of operators, and then we have here product of operators sandwiched inside the pure states. So what we can now do is that we can define an operator R1, so, or a matrix R1, and it's going to have rows and columns labeled by, and for simplicity we'll just start by first order monomial, so just by P's, Q's, and identity. So this is going to be the first row labeled by this one, then we have P0 given 0. Then there's going to be a lot of things, and P and A given 0. And there's going to be P0 given 1. Even more things, and we go to P and A given nx. And here I'm going to be less delicate and just go to Q B given Y. Now, don't see these as operators. These are now just labels for columns, okay? They're like 1, 2, 3, 4, 5, 6, 7 or something. They just label the columns. These are not operators now. Here they're operators. Here they're just like labels. This is how I label the columns, and I will label the rows in the same way. And now I can start constructing a matrix of this type. Because as you can see, this matrix, it has rows and columns labeled by I and J, but you can also just, instead of I and J, label them by Si and Sj, which is essentially what we're going to be doing here. So here we are going to have psi identity times identity psi. The next one is going to be psi, and now the row index is identity times P00 psi. The next one is going to be psi, so there's dots between these, identity times P and A0 psi. The next one is going to be psi, the identity comes from the row P01 psi. Then we have identity here, and P and A and X psi, and then we have that's the first row of the matrix. The second row is going to be the same, but you see, this thing is always coming here. So now this thing is going to be coming there, this operator. And also here inside the matrix, it's an operator. Outside of the matrix, it's a label. Okay, so you can see that this element corresponds to this label and that label, but you have to translate them from label to operator, because we, in the end, know how to do that. Now the same thing, but we have to use this label. I feel like an old school printer Have you ever seen those printers that go like,
I think we all got the point, so I don't think you have to continue writing everything down. You can just...
No, I need to, sorry. And that's it. Now, I will call this matrix R1. So this thing inside, without the labels, that's a matrix R1. And thanks to this lemma, I know that R1 is a positive semi-definite, because it's just a matrix of that form. Now, we can start using these rules as constraints on this matrix. So, am I making it obvious, or do you all already know where this is going? Okay, so constraint number 1 just says that the state is normalized. So, you apply the 1 here and say that this is equal to 1. Constraint number 2 tells us that if we sum over the projectors here, we always get a thing. So how does the number 2 work in this matrix? So from now on, this will be a yellow constraint. Yeah?
You can replace the P and A things by 1 minus the ones before. Or not 1, but...
Yes. Yes, but the way it's usually done is that you enforce that these things sum to 1, because they just sum up to this thing, These things would sum up to that thing. These things would sum up to that thing. Because you see, there's 0, 0 to NA0. There's also 0, 0 to NA0, which means that these things would also sum up to that thing, and so on. Also here and here. And of course, the same thing will start happening here for the Qs, and here, and so on. Will this be the case anywhere else? Exactly, and that's this thing summing up to that thing, right? So in this way, we exhaust all possible ways to apply rule number 2. Or we can go through the whole matrix and exhaust all of the ways to apply rule number 2. Rule number 3. First of all, it tells us that actually this thing is the same as that thing, but also that this thing is equal to 0. The same thing happens here. This thing equal to 0. This thing the same as that thing. The same thing will start happening here inside of these terms and in all of the other terms. So you just always look for a series of operators where you have two p's next to each other with the same label x and reduce it according to this, which just means it's equal to something that you've already seen before. That would in principle exhaust this rule. And the rule number 4, that's why I also had to write this part, because it tells us that these two things must be equal. That's this one. But moreover, this is equal to PAB given xy. The same thing happens here. The same thing happens here, and so on. And in this way, we can exhaust all possible applications of the rule number 4. Okay. So in the end, what are we left with? Or how to use this to determine whether given PAB given xy can or cannot be obtained from a commuting measurement strategy. This thing would be also connected to this thing. So what's the strategy now? The problem is that I give you this, but you don't know whether it's of that form. I was talking about this now for a considerable amount of time because I was claiming it will somehow help to address the issue, and now I'm asking for the last step, like how to do this. How to use all of this. What is the strategy now?
The probabilities are real, right?
Usually.
And I don't see that we already have used the commuting property. Because for real probability, yeah, but if P is real, in Q and large P both are self-adjoint,
yes,
we get property 4 for free, even if they don't commute, I think.
Okay, yeah, there should be like with operator M1 here and operator M2 here, and operator M1 here and operator M2 here, and then it's not equal to that anymore.
Yeah.
So yes, that's true. The more complete way to write down property number 4 would be to say that you should have operator M1 here, then you have PA given x, QB given y, for operator M2 here, and that must be equal to the same operator, then you go QB given y, PA given x, the same other operator, and psi. And the same thing happens here, that you can always put an operator here, and then you get the same operators around here, you know? But of course, then this is not equal to PAB given xy unless the M1 and M2 are identities or they're exactly equal to that and that.
since we don't have any M1 and M2 there, we still don't use the commuting property in our matrix.
Okay, not at this point. Okay, I agree that in principle the equality of, that this is the probability and that's the probability, hence they must be equal to each other without using the commuting property. Yes. Okay, that's a good point. I'll comment on the commuting property a bit later. So what we did is that we said that we have this thing and we want to check whether it's of that form with this constraint. We start and we said like, okay, now assume that that's true. So if this is true, then we argued we can go to pure states and projective measurements, or at least I said that an argument such as that can be made. So we said, okay, now we have pure states and projective measurements, and we derived some rules here, and then we said like, okay, look, given this, you can construct the positive semi-definite matrix like that, where there's some kind of relations between the elements of the positive semi-definite matrix. So if this thing is of that form, which we don't know, but if we assume that it is, then we can find a positive semi-definite matrix with some kind of relations between those entries, moreover, with the input data being present inside the matrix. So what do we do now to check that whether this is true or not? Yes?
Check if the matrix is positive.
Or check if such matrix exists. So now the strategy is as follows. Step number, oh no, I already used that type of numbering. Step number 1, we get PAB given XY. Step number 2, initialize initialize matrix R1 of sufficient size such that 1, 2, 3, 4, these things are enforced as constraints, okay? So I'll just say that now I take a big matrix, some of these entries are going to be given to this PAB given XY. Some of these entries, for example, such as this one, I can compute from that, because you know that this QB given Y psi is nothing else than sum over A of PAB given XY. Which you can prove by plugging that expression in. So some of these entries are exactly the input data, some of these entries can be computed from the input data, and which entries are there going to be any free parameters now, at this point, for this matrix? So I'm claiming that if I initialize the matrix, and I enforce these constraints, that then some elements of the matrix are going to be exactly equal to the input data that I have. Because that corresponds to these elements. Some of the entries of the matrix are going to be equal to sums or functions of the input data, because, for example, this entry here will be the sum of all of these entries. So if you combine the purple and yellow rule, so the purple rule tells you what are all of these entries in terms of that, and the yellow rule tells you that this is sum of all of those before, which means that you can exactly compute this one. But now I'm asking, like, is there going to be any free parameters in this matrix? This one. This somehow tells you what is the probability of Alice, something like first measuring that and that, or it's not even a probability because it's not going to be a real number. But this thing, we don't know what it is. If we are given just this conditional probability, we have no idea what that is. So we initialize the matrix, which is just now a matrix of numbers, such that the rules corresponding to 1, 2, 3, 4, what we have all here, are enforced. And with some 3 parameters. And the 3 is check whether R1 positive semi-definite is possible. And now this is important to realize that this is not a trivial constraint. Okay? Because we already know some information about the matrix. It's like, think of it as a Sudoku. Like this matrix R1 is like a big matrix of numbers. Some of these numbers are pre-filled from the input data. Some of these numbers are computed from the input data. And we know that some of these numbers must be equal to each other or the sums of the other ones or something like that. So there's like a lot of constraints inside the matrix. And now making it positive semi-definite and obey all of those constraints is a non-trivial thing to ask. Okay. So now if there exists R1 that is positive semi-definite, then what? And if there doesn't exist R1 that's positive semi-definite, then what? Yes?
Well, then the probabilities don't have this form of trace density operator.
So which then is that? Is that then?
Well, it does not exist if it's not semi-positive.
Yes.
I'm a little confused because I thought this lemma told us that R will be positive already existed.
Well, it will be if these probabilities comes from that. Okay, if R1 is, well, you have to understand, here we constructed the matrix if we assume that this is true. But now we are just given this input data and we don't know that it's true anymore. This PAB given xy and this PAB given xy are two completely different things that are usually denoted the same thing. But we should call this as a, we should see this as a completely different list of numbers than that one. So if it exists, then what?
Well, then these operators P and Q exist.
No. Then I like the reaction of your colleague, then we don't know. Nothing. Because we know that if these operators exist, then we can construct that matrix. But if we can construct the matrix, doesn't mean that the operators exist. It just means that we can construct the matrix. So then we don't know. There's one thing that we can do, is that so far we were using a list of operators like this. One can say that, okay, now let's extend the list of operators by adding products here. Maybe products of also P's and Q's. Okay, so up there we did this. Now we can say that, well, if that didn't work, we can always try the same thing, but we can just try to add more rows and more columns, you know? This will give you more constraints, more stuff to play with, more hope that something's going to break and the matrix will stop being positive semi-definite. And if that doesn't work, you can also always start going to even higher orders. Okay, so what's going to happen is that here we had this list of operators and we made it label the rows and columns and got some conditions. If it fails, then that's nice. If it doesn't fail, we don't know. But in that case, we can at least say that, well, but now we can try also adding products of operators or monomials of higher order, or in other words, words in operators when we see this as an alphabet. And that will give us more condition conditions. And if that doesn't work, we can try even more and more and more and more conditions until it works. And because this R1, in mathematical terms, this is called the Gram matrix, you can actually prove that if you would somehow keep going with this to infinity, and it always works, then your conditional probability must be given by commuting measurement strategy. But you would have to go to infinity, which takes infinitely long time and infinite energy, so don't do that. If for all k here, for words of arbitrary length, if these operators, the matrix would always exist, it would converge. This somehow tells us that this is a good idea, or this tells you that this hierarchy cannot be made significantly better, but of course, there's many ways to improve this. Also, enforcing all of these constraints or coding this for arbitrary level k is non-trivial and takes way more thought. So please just take this as something like a very brief introduction to the NPA hierarchy. Like now you know the basic idea, but there's way more stuff that people do here. Because for example, one of the most, or one of the nice things that people do, or one of the basic things is when you take the level 1 plus AB, so you take just this operator and these operators. I can again construct such a matrix. In fact, you don't always have to go for complete list. You can, for example, say I take this one, and I don't know, this one, and I can again construct the matrix. You know, you don't have to include all of the rows or all of the columns. So there's way more theory behind this than I'm just telling you now about. Are there any questions? By the way, we can also flip this around, because if you would like to optimize a function over all probabilities that you can, over all conditional probabilities that you can obtain in a quantum theory, then you can also, so if you would want to optimize over PAB given xy given by this expression, that's a very hard problem. But what you can do is that you can fix a certain level of the NP hierarchy. You can now see PAB xy as your variables, not as something you get. And you can say that, okay, I'm now going to optimize over PAB xy such that there always exists this matrix R1 that's positive semi-definite, which doesn't mean I can realize them in quantum theory, but it's like a bigger set, you know? So, what happens is that we then have these quantum ones, and then we have those ones for which there exists a matrix R1, which is a strictly bigger set. But if you want to optimize over these probabilities that you can obtain in quantum theory, that's a very hard problem. But you can always optimize over this set R1 or over the set RK. And this is how this comes into play in quantum key distribution, because you want to optimize over those things. But that's somehow flipping the logic a little bit around. It just takes maybe a quiet 5 minutes to think about it. By the way, if you ever need to use this, please check for available software packages. People have already coded this and spent a lot of time doing that. So, and it's on GitHub, usually in Python or Julia, so please do that. Like, it's nice trying to do this for yourself. It might be a nice exercise, but also if you want to just get results fast, there's stuff online for that. With that, we are finally reaching the last part, or the last topic of this lecture, which will be about quantum networks. We have so far already discussed many of the aspects like entanglement, bell violations, teleportation, how that may be used for entanglement swapping and all of these things. And now we'll look at quantum networks. Now, this can mean two things, and two very different things. The first thing that usually people mean when they say quantum networks is what we would like to call quantum internet. Which is, of course, chosen so that it's as a name so that it sounds good on funding proposals. Now, what this would be like a network connecting quantum computers in different cities and different parts of a city and different countries, all connected with quantum links so that they can exchange quantum information coherently. And that would be useful for quantum key distribution or distributed quantum computing, blind quantum computing, and so on. So what would be going on here is that we don't want just to have some kind of simple experiment where we generate an entangled photon pair and then measure it in a fixed basis. But what we would like to want is that we would like to want to have a source of, say, Bell states, because of course, what else? That would be connecting two quantum computers. So say this one can be in Hanover, and the other one can be in Berlin, such that this link will be able to create entangled pairs between these two quantum computers. These two quantum computers will be able to somehow take the entangled photon and put it inside of them, which is a non-trivial thing for a quantum computer to do. And moreover, in such a way that the entanglement is not lost, well, obviously. And of course, we have to have some kind of classical channel that can go back and forth between them so they can tell each other what they're doing classically. Of course, we don't want to do this with just two CTs, but we in principle want to add more quantum computers, more CTs. We can have some kind of non-trivial network topology, and so on. Well, this should be. And so on. So, and this would be like a quantum internet where you can create secure quantum keys between all of the participants, but also maybe here in Hanover we will have like a very nice fancy big quantum computer, but maybe here in Munich they would not be so good at building them, so they will have just a very tiny quantum computer and they would want to run something very big. So what they can do is that they can actually send us some kind of instance of their problem, or we can somehow run a subroutine for them and send it back to them. Or even better, we can run the subroutine and teleport the result inside of their program or stuff like that, which would be a distributed quantum computation that you could do in such a network. You can also do a blind quantum computation, which is an interesting thing where the guys with a small quantum computer would actually ask us to calculate something for them, but they can do it in such a way that we don't even know what we would be calculating. So they basically send you like the data and you process the data, but you don't know what the data is. So I don't know if this is like a GDPR heaven or GDPR nightmare, but one of those, maybe a superposition. Why don't we have this?
We would need working quantum computers for that.
We have those. With 5 to 10 qubits is fine.
It's not useful.
Yeah. Well, I mean, quantum key distribution between banks and like government organizations and army stuff could be probably nice.
We don't have the cables which can transport photons or something like that.
Okay, I know that this is a new thing in Germany, but you can have like a fiber optic internet. When I moved to Hanover, I was trying to get one, and they explained to me that this takes a very long time because it's such a new technology in Germany. I think the technology is older than me, but I take that as a compliment from the German system. So now we do have fiber optic cables that we could use to transfer photons, and you could use photons that are of the correct wavelength to work in the fiber optic cables, and so on. What's the distance from Hanover to Berlin?
Around 300 kilometers, I think, plus minus.
Sounds about right, because it's like 2 hours by IC.
Yeah,
Yeah. Okay, so here's one of the problems. If you send a photon through this fiber optic cable, it's not perfect. It will start decohering and things like that. And in principle, after 150 kilometers, it's almost gone, or it's not practical anymore. Which means that you cannot just say between here, just have like something like this. But here in the middle of the links, you would need to have repeaters. So basically, this would create a bell pair here, and then it would do the entanglement swapping, which is just do teleportation on 1/2 of the bell pair. And the same here and here. Of course, this is not perfect and it incurs some kind of noise. Moreover, the quantum computers, like what technologies used to build quantum computers? I mean, you have a lecture on quantum computation, right? On Mondays.
Quantum information.
Oh, okay. But you did like quantum computation there, right?
Not the experimental part.
Okay. So, have you heard about anyone building quantum computers? Whom? Where?
Like high-tech here.
Like what?
Building high-tech, like here.
Oh yeah, like the building over there next to the cemetery. Okay, how do they do it? They use trapped ions, and they want to build 8 trapped ion quantum computer, or at least the group I heard of that. So trapped ions, neutral atoms, photons, photonic quantum computers, and so on. So assume a trapped ion quantum computer. This is a photon, and here inside the quantum computer there are trapped ions. Now there's a problem. A photon is not a trapped ion. So if you want to take the photon and actually move it inside of the quantum computer, you somehow need to take the quantum information, the quantum state of the photon, and swap it with the quantum state of a trapped ion, or basically get it over, you know? You cannot just read it and then, you cannot just read the state of the photon and then prepare the respective state in the trapped ion, because that would destroy any coherence that you have, because you would be performing a measurement. So you need to do this coherently. That's hard to do. Okay? All of these operations, all of these things are incurring noise, and given that there should be a lot of links and a lot of potential sources for noise, these effects multiply and they add up together, and in the end it's like really, really hard to do, exactly and only because of the noise. In a noiseless world, this would be like really easy to build. In the real world, this is incredibly hard. Nevertheless, people are trying. There's, for example, the Quantum Internet Alliance that's trying to do this in Europe. People are building nodes and testing connections on ever longer distances, so we'll see what happens. The second thing that people would call quantum networks, and the thing that I want to talk about more in the next 2 lectures, or how many we have? 2, right? Yeah. Is something that are something like Bell-like experimental setups. With more parties. So, what was one of the main problems in Bell-type experiments? The practical part.
Taking the entangled particles.
Yeah, but that was already done in like 70s, 80s. Yes?
Avoiding loopholes.
Yes, exactly. This is something we discussed before Christmas, is that if you do your data processing wrong, then you can open some kind of loopholes where you can say that, look, but if you do the data processing like this, I don't even need quantum theory and I can maximally violate HSH inequality, even beyond quantum theory. Which just means that the step you're doing is not a valid step that you should be taking in this kind of settings. And one of these loopholes was coming from the fact that there are inputs. So in the usual Bell-type experiments, Alice and Bob measure some kind of measurements and they get outcomes, but they don't measure just one fixed measurement, but they have more measurements, okay? So usually we have PAB given X, Y, and these things, this is the input of Alice, and this is the input of Bob. And one of the things was that if Bob's measurement would know the input of Alice, then they can exactly violate HSH as much as they want, because then essentially Alice would be just performing a single measurement. Now, this was somehow solved by changing the measurement basis or the measurement setting or the input randomly and fast enough. First it was done fast enough, then it was done fast enough and randomly. But still, this is something like a technical problem that we have. Wouldn't it be nicer if we would just drop the inputs? Just measure one thing, you know? So instead of that, we just go to P of AB. Now, for two parties, does this carry any quantumness whatsoever? So the assumption that we had was that we have Alice and that we have a Bob, and we have some kind of source in between them that's sending something to them. And if the source will start sending them quantum states, so entangled quantum states such as the Bell state, then they can, for example, violate the CHSH inequality or other Bell inequalities. If the source will be sending them just classical information, so something like density matrices which are diagonal in the computational basis or in the product of the computational bases, then they cannot violate any Bell inequality because they don't share any non-local resource beyond some kind of shared randomness, so some kind of shared classical correlations. Now the thing is that if you want them just to do a one fixed probability distribution, just say to this source that, hey, you will be sampling from this probability distribution and sending the respective labels to Alice and Bob. They just output the label that they have, no quantum stuff involved, and what they'll be outputting is exactly this probability distribution. So for two parties, you cannot drop the inputs, and they are key to doing anything that's beyond classical theory. Is that understandable? You can even try to play this game just somehow by yourself, or you can even maybe with a friend or with two friends, that if you just fix the probability distribution, you can always just sample from it, tell each other what the sample is, and just output that thing, and it will always recover exactly that probability distribution. So what we do is that we add more parties. But here's the thing. There's two ways to add more parties. We can add more parties like this, that there's going to be a single source sending stuff to all three of them, and we can add more parties like this. That each pair of them shares the source. Which one is the one that we want to go for?
Like the picture you've drawn seems more like the second type, but my initial idea would have been the first type.
Oh,
just because
wait. That thing is a completely different topic to this thing.
Never mind, I didn't say anything. The first one I would go for because I think there would be less possible ways for errors. That's true, but now the question is, if we would do this kind of so this thing and that thing, what the difference is what one would call topology of the network, you know? So where does the information come from? And in this case, if I have a single probability distribution of probability of Alice observing outcome A, Bob observing outcome B, and Charlie observing outcome C, is there something I cannot realize here? You see, what stopped us here is that if I choose any probability distribution between Alice and Bob that doesn't have inputs, so just this thing, and I have single source between Alice and Bob, then they can start outputting from this probability distribution completely classically, because the source does all of the work and Alice and Bob just output whatever the source tells them. Now if I do the same with three parties, and I have a single source, see the problem? The source will just sample from this probability distribution, send the label A to Alice, label B to Bob, C to Charlie, and just start outputting. So for example, I can say that I can have P000 equal P111 equal to 1/2, which is a valid probability distribution with Alice and Bob having outcomes in 0, Alice, Bob, and Charlie having outcomes in 0 and 1. The source will just toss a coin or generate a random bit and send the value of bit to each of them. And they just output exactly the value of the bit. And they'll be sampling exactly from this probability distribution. So if we would choose this topology, we have exactly the same problem as here, because everybody is connected to the one and the same source. But here, oh boy, here it gets different. Here, so the first thing that you can think about is whether this probability distribution is possible in this network topology. Is it? So this is a probability distribution that's completely concentrated at one point, which means that I want a scenario here such that these sources are sending classical information to Alice, Bob, and Charlie, and I want everybody just always to output 0. How do we do that?
Just send zeros.
You don't even have to send anything, just say 0. Just, if you want this probability distribution, you don't even need the sources. Just say to Alice, like, Alice, whenever ask a question, you're going to say 0. Bob, whenever ask a question, say 0. Charlie, whenever ask a question, say 0. So if you say like, okay, guys, now measure, everybody just tells you 0. This is the same thing, but I exchange 0 for a 1. But the 0 and 1, they're just labels. Can I do this thing in this scenario? Yeah?
Which of the two arrows pointing to ABC correspond to the label?
No, this is just a source of classical information. This node can generate any random number from whatever distribution you want and sends a function of that random to Bob and a function of that random number to Alice. And you can choose the function. Bob receives that thing from this source. So usually I would call this source alpha, this source gamma, and this source beta, because the source alpha is opposite of A, gamma opposite of C, beta opposite of B. So Bob will receive something from source gamma, something from source alpha, can compute it in any way he wants, and just outputs 0 or 1 based on that. Also, Bob can generate random numbers if he wants. So this easy. Can we do this in this type of a network?
I have a question. Don't they get two measurement results? And they are given two sources.
Yes.
And we had like 2 bits.
Yes, and you somehow have to process it into 1 bit. Or like this doesn't even have to be a bit. Like this source can send to Bob like the whole, I don't know, some very long book. It can send the collection of all of the works of Immanuel Kant or something. It's fine, you know. You can send as much classical information as you want. Continuous classical information. All right, I guess this is something to maybe think about for the whole week. And I'll tell you next week.
I don't understand.
You don't
I can't. You said Alice could generate random numbers as well, right?
Yes.
So I could just tell Alice to flip a coin every time I ask her a question.
Yes. So Alice flips a coin. What do Bob and Charlie do?
Flip coins.
Okay. So in that case, what's the probability of observing this outcome? Yeah. And in fact, that's the probability of any other outcome. But here, what we want is that they always output the same thing, all 3 of them. It's completely random whether it's 0 or 1, but it's always perfectly correlated between all 3 parties. Yes?
My first idea was on similar things, but I noticed myself that it wasn't quite right. One question I would have is like, are we asking them all at the same time? Like, when one person asks, are all persons asked? Because then we could just say, yeah, do it alternating. But I don't think that is what we want, and I don't think it's in that direction.
No. That's I really like it because the last September there was a scientific talk which exactly said that this is a problem that we might have in quantum networks. if the detectors remember the previous answer. Because yes, what you can do here is that you say like, whenever you are asked first time, say 0. Whenever you are asked second time, say 1. So you just always output the parity of the number of the questions you were asked. At which point you would be effectively getting this, but it's not like a random, truly random number that you are getting out. So for that reason, one should assume that this should work in like a single shot, and that they cannot remember what happened before or after. Like maybe we like somehow hit them with a hammer on the head so they forget, or I don't know. So to restate the problem, it's like this. We have 3 sources, alpha, beta, and gamma. Alice will receive information from the source beta and gamma, but not alpha. Bob will receive information from alpha and gamma, but not beta. And Charlie from alpha and beta, but not gamma. Now, these sources, they can generate random numbers. They can process them however you wish, and then send that to the respective parties connected to them. Each party will receive information from 2 sources. This information can be as big as you want, as long as it's classical information. They can process it in any way they want. They can also generate random numbers. And the question is whether they can output this in a single shot.
I have a maybe idea.
Yes?
Like, maybe like for 2 people, it's like if those 2 are different, do that thing, and if for the last person, I think if the 2 are the same, do the other thing. And like then you can maybe get that if, for example, 2 are then 2 are doing this information and the third is doing that information, that for all are 1 and for all are 0, and I can imagine one finding a way to do it like this then.
Try it out.
I can try it. Yeah, okay.
Please do.